We spend a lot of time talking about whether a function is going up or down. But what if we could understand its actual shape? Today, we're going to dive into the geometry of curves and really uncover the hidden story that's being told by all their bends and turns. So here's our game plan. We'll start with the basic idea of a curve's geometry, and then we're going to give that bend a proper name, concavity. After that, we'll unleash a really powerful tool, the derivative test, to measure it. Then we'll hunt for these super interesting inflection points where the curve's whole personality changes, lay out a step-by-step method to find them, and finally, we'll tackle a few tricky special cases that'll really test our understanding. Right, so we all know the first derivative tells us about the slope. Are we heading uphill or downhill? But that's really only half the story. It doesn't tell us how we're getting there. Are we curving gently or are we turning sharply? That's the question we're getting into today. And this right here, this is the big question for today. How do we take that gut feeling we have about a bend and actually describe it with some real mathematical precision?
Just take a look at these two curves. Sure, they're both increasing on one side and decreasing on the other, but they are so obviously bending in completely opposite ways. Curve A opens upwards, and curve B opens downwards. We need a formal language for this difference.
And that formal language we've been looking for? Well, it's got a name, concavity. This is the exact mathematical term we're going to use to describe the direction of a curve's bend.
So here's the official definition. A function is concave up when its slope is always increasing. Just picture a parabola opening up. The slope literally goes from negative to 0 to positive. It's getting bigger. And the opposite is concave down, where the slope is always constantly decreasing.
Now here's a fantastic visual trick for a concave up function. Any tangent line you draw will always sit below the curve itself. A really easy way to remember this is to think of it like a bowl that's right side up. It can actually hold water.
And for concave down, you guessed it, it's the total opposite. The tangent line is always sitting above the curve. This is our upside-down bowl. It's just going to spill water. Seriously, these visual checks are super helpful. Okay, so that whole bowl analogy is great, right? But let's be real. We can't just sit around drawing a million tangent lines to test a function. We need something way more powerful. And that tool is the second derivative test. The second derivative, f double prime, is basically our official shape detector. It measures the rate of change of the slope. And since we just defined concavity by how the slope is changing, this is literally the perfect tool for the job. And the rule itself? It's just beautifully simple. If the second derivative is positive in some area, the function is concave up. Think of it like a smile. If it's negative, the function is concave down, like a frown. The sign of f double prime tells us everything we need to know about the shape. It's that easy.
But hold on. Here is a really critical point of caution that comes straight from our source material. This is a one-way street. Just because a function is concave up, it does not automatically mean that its second derivative has to be positive. That is a subtle but super important distinction to keep in your back pocket. So, we have concave up, we have concave down, but what about those exact spots where a curve switches from one to the other? These really critical transition zones have a special name, inflection points.
Now, an inflection point isn't just any place where the bend switches. As you can see from the definition here, it's a point where that change happens and the function is smooth enough to have a well-defined tangent line. Both of those conditions are absolutely required, no exceptions.
So let's just break down what's happening. At a true inflection point, three things are going on. First, the sign of the second derivative flips. Second, a tangent line absolutely has to exist there. And third, you get this really unique visual, where the tangent line doesn't just touch the curve, it actually pierces right through it. It's pretty cool to see. Okay, so the best part about all this theory is that we can turn it into a reliable, repeatable process that we can use to analyze pretty much any function. So let's walk through that exact method right now. Here it is, a simple four-step recipe. First, always know your domain. Second, you got to do the calculus. Find f prime and then f double prime. Third, you hunt for those candidate inflection points by setting that second derivative to 0 or finding where it's undefined. And finally, you build a sign table to map out exactly where the function is smiling and where it's frowning.
Let's put this recipe to the test with an example. F of x equals the natural log of x squared plus 1. So after we do steps 1 and 2, that's finding the domain and the derivatives, we land on this second derivative right here. Now to find our potential inflection points, we just need to see where this whole thing equals 0, which really just means we need to find where the top part, the numerator, equals 0.
And now for the final step, the sine table. This is where the magic happens. Our critical points are -1 and +1, and those split our number line into 3 different zones. By just plugging a test number from each zone into our second derivative, we can see if the sign is positive or negative. A negative sign means concave down. A positive sign means concave up. And you can see it plain as day. Right at -1 and +1, the concavity switches. Those are our inflection points.
So, here's our final analysis. The function is concave down on the 2 outer intervals, it's concave up right there in the middle, and because that concavity changes right at x equals -1 and +1, we know for sure we have 2 inflection points at -1, ln2 and 1, ln2. Boom, done.
All right, now the theory and the standard examples are awesome, but you know, the real test of whether you've got this stuff down comes from the tricky cases. Let's look at one to really sharpen our thinking.
So here's a good question. We know to look for where f double prime is 0, but what about a spot where it doesn't even exist? Could we still have an inflection point there? What do you think?
And this quote from another example in our source material gives us the clear answer. Even if the concavity does change at a point where the second derivative is undefined, it is not an inflection point if the function itself isn't differentiable there. In simple terms, that just means it doesn't have a smooth, non-vertical tangent line at that spot. And having a tangent line, well, that's a non-negotiable requirement for an inflection point.
We've just seen how the second derivative gives us this incredible, deeper look into the geometry of a function, revealing its true shape. It really makes you wonder, right? If this is what the second derivative can tell us, what other secrets about our world are just sitting there waiting to be unlocked by the next level of calculus?